comparing two means. This is the notes for section 10.2. So the sampling distribution of x bar 1 minus x bar 2. We're going to choose a simple random sample of size n1 from population 1 with a mean mu1 and a standard deviation of sigma 1, and an independent simple random sample of size n2 from population 2 with a mean mu2 and a standard deviation of sigma 2. When the population distributions are normal, the sampling distribution of x bar 1 minus x bar 2 is also normal. In other cases, the sampling distribution of x bar 1 minus x bar 2 will be approximately normal if the sample sizes are large enough so they both have to be greater than or equal to 30. The mean of the sampling distribution is mu1 minus mu2. That is, the difference in the sample means is an unbiased estimator of the difference in the population means. And the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is the square root of the variance of 1 divided by n1 plus the variance of 2 divided by n2, as long as each sample is no more than 10% of its population. Remember that variance is the standard deviation squared. A fast food restaurant uses an automated filling machine to pour its drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the setting chosen is chosen, the amount of liquid dispensed by the machine follows a normal distribution with a mean 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid dispensed follows a normal distribution with a mean 17 ounces and a standard deviation of 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in a random sample of 25 cups filled with the medium setting and a separate random sample of 20 cups filled with the large setting. Let x bar 1 minus x bar 2 be the difference in the sample mean amount of liquid under the two settings, large minus medium. So I'm going to start by going through and highlighting what goes with the medium and what goes with the large. So under the large setting, there's a mean of 27 ounces and a standard deviation of 0.8 ounces. And it also follows a normal distribution. Whenever we are taking the random sample, we're going to take a separate random sample of 20 cups filled with the large setting. Alright, I'm going to do the same thing for medium. So a medium setting is going to have a mean of 17 ounces, be approximately normal, have a standard deviation of 0.5 ounces, and I'm taking a simple random sample of 25 cups. So for number 1, it says what is the shape of the sampling distribution of x bar 1 minus x bar 2 and why? So I'm going to refer back to the information that we covered on the last page, and it says the shape when the population distributions are normal, that the sampling distribution is normal. So both of these told me that they were normal. So x bar 1 minus x bar 2 is normal. And it may be useful to say that this is because the population distributions were normal. 2 says find the mean and the standard deviation of the sampling distribution. So basically we're finding mu of x bar 1 minus x bar 2. So we're going to refer back to the notes we covered earlier. And so it says the mean of the sampling distribution is mu1 minus mu2. So I'm going to use 27 minus 10. Now I got that because the mean for the large setting was 27 and the mean for the medium setting was 17. It told us we were doing large minus medium. So large being the 1s and medium being the 2s. So when I do that, 27 minus 10 would give me, actually no, oops, this is 17. And that gives me 10. So 27 minus 17 gives me 10. All right, now I do my standard deviation for x bar 1 minus x bar 2. Again, refer back to the notes here. And so I'm doing the square root of the variance over the n1s and the n2s. So the square root, remember the variance is just standard deviation squared. So I'm going to do 0.8 squared divided by n1. And n1 is going to be 20 because my ones were my large ones. And so I'm choosing 20 for my sample for large, and for N2, which was my mediums, I'm choosing 25. So then I add to that the mediums. So the medium had a standard deviation of 0.5, so I square it, and then I put it over 25 because that's the number that was in my sample. Whenever you do that, you get 0.205 ounces. Three asks us to find the probability that x bar 1 minus x bar 2 is greater than 12 ounces. All right, to get my z, which is what I would need to be able to look on the table and find out what my p-value was. I would say 12, because that's the number I'm worried about, minus the mean, divided by the standard deviation, the 0.205. And whenever you do that, you get 9.76. You would look on the table, and whenever you do that, you would get the p to be approximately 0. You can also do this on the calculator by doing second vars, doing option 2, normal CDF. Your lower bound would be 12 and your upper bound would be positive infinity, because remember, you are trying to say that this stuff is greater than 12, so 12 would be the lowest that it could be. Whenever you do that, you get this number. This part means you move this decimal back 23 places. So whenever you do that, you get something that's essentially 0. Number 4 says, based on your answer to question 3, would you be surprised if the difference in the mean amount of liquid dispensed in the two samples was 12 ounces? Explain. So you would say, since the probability in number 3 is so low, so small, we would be very surprised to find a difference of 12 ounces. Sample 2 or 2 sample t interval for a difference between two means. When the random, normal, and independent conditions are met, an approximate level C confidence for x bar 1 minus x bar 2 is x bar 1 minus x bar 2 plus or minus t star times the square root variance 1 divided by n1 plus variance 2 divided by n2. Here, T star is the critical value for the confidence level C for the T distribution with degrees of freedom from either option 1, which is using the calculator, or option 2, the smaller of the N1 minus 1 and N2 minus 1. So when we're checking to see if it's random, the data are produced by a random sample of size N1 from population 1 and random sample of size N2 from population 2, or by two groups of size N1 and N2 in a randomized experiment. Normal, both population distributions, or the true distribution of responses to the two treatments are normal, or both sample group sizes are large, so both of them are greater than or equal to 30. And independent, both the samples and the groups themselves are and the individual observations in each sample or group are independent. When sampling without replacement, check that the two populations are at least 10 times as large as the corresponding samples, and that would be your 10% condition. The U.S. Department of Agriculture, the USDA, conducted a survey to estimate the average price of wheat in July and in September of the same year. Independent random samples of wheat producers were selected for each of the 2 months. Here are the summary statistics on the reported price of wheat from the selected producers in dollars per bushel. Construct and interpret a 99% confidence interval for the difference in the mean wheat price in July and in September. Alright, so to start, we would let July be our 1s and September be our 2s. So this would be X1, this would be X2, this would be N1, this would be N2, and this would be S1 and S2. So we are going to start with that formula that we had on the last page. So that was X1, or X bar 1 minus X bar 2, plus or minus T star, square root, variance for 1 over N1, variance for 2 over N2. Probably the easiest way to do this one is on the calculator. So because it tells us we're trying to find a confidence interval, that means that we are going to use the int, one of the int tests on our calculator. So we're going to go over to tests, and we're going to go to the one that says 2 sample t int. And the reason that we are using 2 sample t int is because it's asking us to find a confidence interval. We have 2 samples, and we use the t because here in our problem we had, or in our formula that we were using, we had the t value. So we use stats, and we're going to just plug in the stuff that we know. So we know X1 is 2.95, we know S1 is 0.22, and N1 is 90. X bar 2 we know is 3.61, S2 is 0.19, and N2 is 45. Change our confidence level to 0.99, and we're going to say no, it's not pooled. That gives us an interval of negative 0.7561 and negative 0.5639. The book answer and the calculator answer are a little off. Of course, they usually are. The book is calculated by using the table, and then we did it by the calculator, but they basically are the same thing. So the way that we would interpret that is we would say we are 99% confident that the interval negative 0.759 to negative 0.5639, so 4, captures the true difference in July to September. Suppose the random, normal, and independent conditions are met. To test the hypothesis, null hypothesis, where mu1 minus mu2 equals the hypothesized value, compute the two-sample t statistic using this formula here. Find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis. Use the t-distribution with degrees of freedom approximated by technology or the smaller of n1 minus 1 and n2 minus 1. Conditions: use this test when the data are produced by a random sample of size n1 from population 1 and a random sample of size n2 from population 2, or by two groups of size n1 and n2 in a randomized experiment. Normal: both population distributions or the true distributions of responses to the two treatments are normal, or both sample group sizes are large, so they both have to be 30 or greater. Independent: both the samples and groups themselves and the individual observations in each group or sample are independent. When sampling without replacement, check that the two populations are at least 10 times as large as the corresponding samples, and that would be your 10% condition. How quickly do synthetic fabrics such as polyester decay in landfills? A researcher buried polyester strips in the soil of different lengths of time, then dug up the strips and measured the force required to break them. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed. For one part of the study, the researcher buried 10 strips of polyester fabric in well-drained soil in the summer. The strips were randomly assigned to two groups. 5 of them were buried for 2 weeks, and the other 5 were buried for 16 weeks. Here are the break strengths in pounds. Do the data give good evidence that polyester decays more in 16 weeks than in 2 weeks? Carry out appropriate tests to help answer this question. All right, in order to do this problem, you can use the calculator, and you would use a two-sample t-test. All right, so I know that the test that I would use is a two-sample t-test. So what you would need to do is, the first thing you would have to do, since it doesn't give you any information about the x1 and the x2 and the n1 and the n2, but it does give you the table, is you would need to go and create that table. So to do that, you would do stat, and you would do edit, and then you would have your L1 and your L2. I have already created the table so that it would be ready for the notes for today. But you would need to create those by clearing out anything that was in L1 and L2, and then put in all your group 1s in L1 and all your group 2s in L2. Once you get that, then you can go back out to stat and to tests. And for your test, you're going to do the 2-samp t-test, which is option 4. And this time, instead of using stats like we have been doing, you're going to use data because you have created that table. You're going to leave your list 1 L1 and your list 2, L2, keep your frequency where it is, and then you're going to have to figure out based on the information in the question whether or not you want your mu1 to be not equal to mu2, less than mu2, or greater than mu2. So using the question that you're given in the problem, it says basically that you want to know if there's more decay in 16 weeks than in 2 weeks. And so because 16 weeks was our 2's, then we would want our M2 to be bigger than our M1. So that means that I'm going to choose the one in the middle, and then I'm going to make sure I say no to pooled and then calculate. So whenever I do that, it gives me my T and it gives me my P, and of course my degrees of freedom, and then my X bar 1 and my X bar 2, and then my standard deviations and all of that stuff. What's going to be important is knowing what you are finding. The test statistic is what you were trying to find, which is the T, and so you would need to know what your T value is. So your T was 0.988, so we'll make it 0.989. And you're going to use that test statistic to help you create or to figure out what your p-value is. To get your p-value, you would be finding the probability that your t is greater than 0.989. And I know it's got to be greater than because of the situation we talked about here. Your p-value is going to have something to do with the p that's here. The p that's here, though, gives you the area that's underneath the curve to the left. But because you want a greater than, you need this space to the right. So all of this is the p that they gave you, the 0.814. But if I want to get this area, I'm going to have to say 1 minus 0.814. So when you go to the calculator and you do 1 minus 0.814, you get 0.186, which is what your actual p-value is. All right, so then because it's asking you to carry out the test, then you should go ahead and do like what your conclude step is. So you would be looking at your p-value and comparing it to your alpha value. Because your alpha is not given, we're going to use 0.05. And so you're going to compare your p-value to that 0.05. So because your p-value 0.186 is greater than 0.05, then you would fail to reject your null hypothesis. So basically what that means is you would say we do not have enough information or enough evidence to conclude that there is a difference in the actual mean breaking strength of polyester fabric that is buried for 2 weeks. And fabric that is buried for 16 weeks.